one simple way, you remember where we came up with the idea of the iteration period bound. Essentially what we said was, look, I can implement the entire thing. If I have enough hardware, in other words, I can implement multiple copies of this hardware and get better throughput. Okay. So let's look at what something like that would look like. One way by which I could do something of this sort is, I do precisely that. I basically create 2 copies of the hardware. So I have x of n feeding in here, and let's say I have x of n minus 1 feeding in here. Now what this architecture effectively means is, x of n minus 1 is also being computed over here, or rather being produced over here, and x of n minus 2 is being produced over here. At this point it is x of n minus 2 and x of n minus 3. The multipliers, coefficients ABC remain the same, the adders structure remains the same, right. The assumption is, at a given point in time, okay, I am basically going to apply x of n to the top filter, x of n minus 1 to the top filter. Okay. I will get correspondingly y of n as the output, y of n minus 1 as the output over here. Okay. At the next time instant, okay, I will assume that I am essentially going to shift through 2 steps of the shift registers. So that after this, the next one that goes in over here is x of n plus 2 and x of n plus 1. Okay. But in order for these intermediate values to be generated correctly, it means that I will effectively have to shift 2 values through the register. So I have to sort of assume that there is one shift register where I can pump through 2 values through it quickly. Okay. So in other words, x of n, there will also be one x of n plus 1 that comes over here, x of n plus 3 over here, and so on, and similarly x of n is over here, x of n plus 2 is over here, so that the corresponding values can then be skipped through into this. In other words, x of n will be here. On the next clock cycle, x of n will go here, and the x of so I have x of n minus 1, x of n minus 2. In the next time instant, I will have x of n over here, I will have x of n plus 1 over here, and x of n plus 2 over here. Okay. So that this will then compute y of n plus 2, right. And similarly, the first time around I have x of n minus 1, n minus 2, n minus 3. The next time around I will have x of n minus 1 jumping over here, x of n over here, and x of n plus 1 over here. Okay. Right. So in other words, the assumption is that the way that the shift registers are implemented is, I am able to sort of skip forward 2 steps. Okay. But that is just an implementation detail in terms of how the shift registers themselves are implemented. All that it means is the sort of forward connections that need to be made between them, it need not necessarily pass through both the registers, it can directly skip ahead and go forward 2 steps. Okay. Why is this important? Because we want to make sure that the top filter is always computing only the even values of y, and the bottom filter is computing only the odd values. I do not want the top filter, in other words, to compute the odd values and throw them away. That would be a waste of computational power, right. So I essentially assume that I can skip forward by 2 steps, so that the top filter can just concentrate on computing even valued y outputs, okay, and the bottom filter correspondingly can then compute the odd valued y outputs. Okay. So effectively what happens in this situation is, once again the t clock, which is basically the critical path, remains exactly the same as before, 4 nanoseconds, right. But every 4 nanoseconds 2 outputs are produced. Okay. and that effectively tells us that our sample period becomes half the clock period. Okay. The average sample period can become half the clock period simply because we have thrown twice the amount of hardware at it. Okay. There is nothing really very fancy about this. All that I am saying is I am throwing twice the amount of hardware at the problem. It is possible to arrange the data in such a way that the computation can actually be done at twice the throughput. Okay. In order to understand this a bit more clearly, you probably want to contrast this with the case of the IIR filter, right. I will leave that as an exercise for you to go through. Try and see if you can do something similar for the case of the IIR filter, and you will find that you cannot because of that dependency, right. After all, that was a dependency that led us in the first place to this concept of iteration period bound, and you will find that in this particular case that prevents you from using twice the amount of hardware effectively. Okay. But in the case of the FIR filter, you can do that. You can put in twice as many adders and multipliers and actually feed the data to them alternately such that the overall throughput doubles. Okay. So, the throughput is number of samples being processed per unit time. Okay. And that ultimately is the most important goal of a signal processing system. Okay. How many samples can I process per unit time? Okay. Not really the clock period at which I am operating, that is incidental. Even if I can operate at a low clock period, but I can process many samples per unit time, that is perfectly fine as long as the number of samples being processed per unit time meets whatever sampling rate that I require.